So this section 5.1, proving identities, kind of goes back to one of our earlier sections when we started kind of establishing the identities. So the first thing I did in these notes is to just to kind of have all the identities that we're going to use in this section right here in one place, and just to review them and refresh them a little bit before we start to apply them in some of the examples. So just to refresh, reciprocal identities, those are your, exactly what they say, reciprocal. So remember, cosecant is the reciprocal of sine. Sine is the reciprocal of cosecant. So we can write cosecant theta as 1 divided by sine theta. And sine theta is 1 divided by cosecant theta. Secant is 1 over cosine. Cosine is 1 over secant. So secant and cosine are reciprocals of each other, as are tangent and cotangent. Easy way to remember these two, you're not going to get mixed up, but to keep from getting these mixed up, remember the C and S always go together, S and C. You'll never have an S and S and C and C. So that's kind of an easy way I remember those. All right, then we have the ratio identities. So ratio identities were the tangent and cotangent, and that's when we break tangent, remember, was y over x, and y was sine, and x was cosine. So sine over cosine is tangent, and since cotangent is the reciprocal of the tangent, if tangent is sine over cosine, cotangent is cosine over sine. So it basically is just rewriting those, tangent as the ratio of sine to cosine, and cotangent as the ratio of cosine to sine. All right, and then we had, remember the Pythagorean identities. This should say identities, not theorem, but it's kind of comes from the Pythagorean theorem. But Pythagorean identities. Most common one, sine squared plus cosine squared equals 1. And we went back in that earlier section and kind of derived where that, or proved that that was true on the unit circle. So anytime you see a sine squared plus cosine squared, that can be interchanged for 1. Remember, there's other ways that can be written, though. If you solve this for sine squared, we subtract the cosine squared over. Sine squared theta would be equal to 1 minus cosine squared theta. And in the same way, I could solve that for cosine squared theta by subtracting sine squared over. So I can also write that as cosine squared theta equals 1 minus sine squared theta. So all three of those say the same thing, just solve for different values. Anywhere you see a 1 minus cosine squared, that can be interchanged for sine squared. And likewise, 1 minus sine squared could be interchanged for cosine squared. The other identities that are considered Pythagorean identities, tangent squared plus 1 equals secant squared, and cotangent squared plus 1 equals cosecant squared. So remember, I can also subtract the 1 over, and this would be the same thing to say tangent squared theta is equal to secant squared theta minus 1. And I could also subtract the tangent squared over and write this as secant squared theta minus tangent squared theta equals 1. All right, and then same thing here. I could subtract the 1 over, and I could write this as cotangent squared theta equals cosecant squared theta minus 1. Or I could subtract the cotangent squared over and write this as cosecant squared theta minus cotangent squared theta equals 1. So literally just with a little manipulating and solving for different, you can really get 3 different forms for each one of those. So all those just give you different substitutions, different equivalencies that you can interchange when that suits your purpose as you're working through some of these examples and proving some of these identities. All right, so you want to kind of keep these handy. The more you use them, the more you're going to learn them, remember them. So let's move on. The next statement here, recall an identity. So if you don't remember what an identity is, basically that's just a statement that's always true. It's true for every single value that you put in for theta or for x or for whatever the variable is. For example, sine squared plus cosine squared equals 1. It doesn't matter what the angle you put in there is. Sine squared plus cosine squared is always going to equal 1. To prove or verify a trigonometric identity, you must do one of the following. So to prove it would be to show that it's true. So for example, in this tangent theta over secant theta equals sine theta, in order to prove that that's true, I would either want to start with the left side and change this and show that this is equivalent to sine, or I would want to start with sine and show that it's equivalent to tangent. So you want to transform the left side of the identity into the right side, or the right side of the identity into the left side. Typically what you want to do is choose the side that's more complicated and simplify it to work toward getting it to equal the other side. So it's easier to start with the side that's more complicated because it kind of falls into place as you simplify that. A lot of times it directs you right into what you're trying to get to. So let's try one just to get started here. So I'm going to start with the most complicated side, which would be tangent theta over secant theta. All right, and so I have to show that this is equivalent to sine. So one strategy that often works is just to, if it doesn't involve sines and cosines already, and that's obviously where we want to get to, is to try to change these into sines and cosines. Okay, for example, there is a path from tangent to sine and cosine through the ratio identities here. Tangent is sine over cosine. So let me start with that. Let's rewrite tangent as sine theta over cosine theta. So I'm just substituting because tangent is equivalent to sine over cosine. All right, in the same way, secant can be rewritten as a cosine function. So I'm going to look up here. So just secant, remember, is the reciprocal of a cosine, so I can always interchange secant into 1 divided by cosine theta. So this becomes that. Okay. Now with a little bit of simplifying, I think I can get this into sine. So let's see. I'm going to go this way, just run out of room. So basically, I'm going to do just a little bit of basic math, basic algebra. So I'm dividing a fraction by a fraction. So remember, when you divide a fraction by another fraction, dividing by a fraction is the same thing as multiplying by its reciprocal. So sine over cosine divided by 1 over cosine is equivalent to saying sine over cosine times cosine over 1. All right, and I see here that common factors cancel out in the numerator and denominator. So basically, this is going to become sine cosine over cosine, and those cosines I can divide out, and I end up with sine theta. So through a progression of equivalent substitutions and just some basic simplifying, using sound algebraic procedures, I have shown that tangent divided by secant is equal to sine. And once I've reached this side, I've turned this side into this side, I've proven what I set out to prove. Now, if you didn't, as I did that, if you were thinking to yourself, I would never have known to do that, be patient, give yourself time. This is stuff that takes just a little bit of practice. The more you do it, the more you see the ideas, the things you can try, the easier it gets. So, be forgiving of yourself, be easy on yourself. Don't give up. I'll give you some more strategies here in the next example, before the next example. And, just try something. Sometimes, even as often as I've done this, I have to, I try something and I see that it's not going where I want it to go. I've got to scratch that and start all over. So it's not an exact science. You just have to kind of feel your way through it and try some different things until it's like solving a puzzle. Okay, before we get to example 2, above example 2, you'll see this box of kind of like your box of helpful tricks that you can use in solving or in proving these identities. So let me just kind of walk through those real quickly here. Work on the most complicated side. I mentioned that one previously. So you want to take the side that's more complex, and usually you can simplify, or even if it comes down to breaking it down into sines and cosines, if they're functions that are not already sine and cosine. But you can take the most complicated side and usually do some kind of a little bit of simplifying, and you have more luck going that way than you do going from the most simplified side to the more complex side. The second one, try to simplify by substituting basic identities. You've got all your identities we put on the other side of the notes there. altogether. So, familiarize yourself with those identities. The more you use them, the more you're going to become familiar with them. But just interchanging things that are equivalent is one of the biggest tricks that you'll use most often. 3, look for algebraic operations such as adding fractions, distributing, and factoring that may simplify the side you're working with. We just did that in the previous problem. On the other side, we had to do a little bit of division of fractions where you multiply by the reciprocal. But you're going to see, like in this problem we're getting ready to do right here in a minute, it looks like some possible distributing that could be done here. So basic processes of mathematical or algebraic processes, it's going to be a big part of some of the steps that you do. If all else fails, try changing everything to sines and cosines. So if there's not if all else fails and you can't really find any way to go with it, you can always take, and I could break this into a 1 over sine and this into a 1 over cosine. I could go that route with it. So you can always try, if nothing else, breaking everything that's not already a sine or cosine into sines and cosines. And the last one, focus on the other side that you're working toward and let it guide your direction. So if I'm going to start, of course, this on example 2, we're going to do it in a second here. This is the most complex side. So I would start with this side and try to work it to show that it's equivalent to cotangent x plus 1. But keeping my mind on this the whole time. So as I'm doing this, I know what I want to get to, so I don't want to kind of lose track. I really want to really keep this in mind as I'm working. It kind of guides the direction I'm going. All right, so let's look at example 2. I just mentioned a minute ago that on the right side, to me, when I see this, my first tendency is to want to distribute. I mean, it looks like a familiar algebraic process that you're used to. And so that's a good way to start. So let's do that. Let's distribute here. So cosine x times cosecant x plus cosine x times secant x. All right, so distributive property done. So let me make a little note over here that all I did there was distribute. Okay, so now I'm looking at this. This is where I want to get to. What stands out to me here, cosine, there's not, the cosecant could be interchanged with the reciprocal function 1 over sine. And that would probably be the route. And I could do the secant over here with 1 over cosine. That's probably would be my next step, is just to do a substitution of an equivalent. So equivalent to cosecant x it's the reciprocal function of sine, so 1 over sine x. And in the same way, secant is the reciprocal of cosine, so I could replace secant with 1 over cosine x. So all I did in this step was kind of documenting how I did each thing, was substitute reciprocal identities. All right. Okay, so now think of this as cosine over 1. And so if I'm multiplying fractions, you just multiply across. Cosine times 1 is cosine. 1 times sine is sine. I'll go ahead and multiply these together as well. Cosine times 1 is cosine. 1 times cosine is cosine. And once I do the multiplication here, I realize that cosine over cosine, anything divided by itself is 1. So cosine over cosine is just 1. And as I'm keeping my eye on what I'm trying to get to, it's looking pretty good because I've got the plus 1. So can I get this to be the cotangent? And the answer is yes. If you look back at your ratio identities, cosine divided by sine that ratio is the cotangent. And so let me state right here, all I did there was simplify. I just multiplied the fractions together. And then here I did a ratio identity substitution. And then of course I just simplified. And I have shown that cosine times the quantity of cosecant x plus secant x is indeed equal to cotangent x plus 1. All right, example 3. So looking at this one, this by far is definitely the complex side. This is the side I want to start with and work toward 1 plus sine x. So as I'm looking at this side, you know, a couple things pop out. You know, cosecant, I can always break down if I had to into sine, it's 1 over sine. But something else that stands out to me, and like I said, don't feel like if you're looking at this right now thinking I would never have known to do that. Well, of course you wouldn't have, because you haven't had practice with this. But as you practice, these tricks are you're gonna the next time you see a similar problem that you're gonna think, oh yeah, maybe I tried that. What I tried with that other problem, I might be able to use with this one. So you're going to become more familiar. So don't be hard on yourself. Don't think right now that I'll never know how to do that. I would never know to do that. It's one of those things that just takes practice. Think of it like a puzzle. Identities can be really fun if you are. I think they are, because it's like solving a puzzle. It's like, I know what I need to get to. I know the answer. I just got to figure out how to get from here to here. And these are the tools that I get to use to do that. I can swap out things that are equivalent. I can simplify the math and the algebra that along the way. Okay, so enough of that. So when I see cosecant squared x minus 1, would it look more familiar to you if you saw this? Because it's really the same thing. It's just instead of an x squared, it's a cosecant x squared. Well, this is just a difference of squares. So just going back to algebra 1, you know how you factor a difference of squares. It's a difference of 2 perfect squares. We break the x squared splits into x times x. The squares of 1 are 1 times 1. In order for these to multiply be a -1, one's got to be a plus, one's got to be a minus. And so it's that difference of squares. X squared minus 1 factors into x plus 1, x minus 1. Well, in the same way, this is a difference of squares. This is a perfect square. It's a cosecant x instead of an x. And this is a perfect square. So I can split the cosecant squared into cosecant x and cosecant x. And I can split the 1 into 1 times 1. One's got to be positive, one's got to be negative. All right, looking at the denominator. Now, I notice that both terms have a cosecant in them. Think of this, just to kind of parallel this to something you did in algebra. You know, what if it was this? You know, and I said to factor this. Well, most of you could look at that and say, well, both terms have an x, so I could factor out an x. And if I factor out an x, the other factor, that's the greatest common factor I pulled out, the other factor would be x minus 1. So it's kind of backward distributing. These multiply back to equal x squared minus x. Same thing here, except instead of pulling out an x, we're going to pull out a cosecant x. Okay, so cosecant x times cosecant x equals cosecant squared x, minus cosecant x times 1 would equal cosecant x. So if you distribute that back, this is what I get. So I factored out the greatest common factor. So in this first step, I just basically factored and factored. And watch what happens now. Common factors in the numerator and denominator divide out. And I am now down to cosecant x plus 1 over cosecant x. Okay, so simplified a lot. Still not where I want to be though. So how do I get from here to here? So here's where keeping your eye on the goal, what you want to get to, is helpful. I need a 1. And as I'm looking at this, I see this cosecant over cosecant. Now remember that this cosecant, the divisor, is not just the divisor of this term, it's also the divisor of this term. So basically, this is the same thing as saying cosecant x divided by cosecant x plus 1 divided by cosecant x. But knowing I see the 1 here, that's kind of what prompts me to realize that this cosecant over cosecant is going to give me my 1. And so it does. Anything divided by itself is 1. So can I get this to be a sine? Well, yeah, because that is what sine, it's the reciprocal of cosecant. So 1 over cosecant is equal to sine. And I now am where I need to be. Let me justify. So here I'm just going to say reduce / simplify. Simplified by reducing, dividing out the common factor. From here to here, I basically just rewrote it in in a different way. I mean, it was the same thing. I just rewrote it. And here I just did simplify and substituted the reciprocal identity. And that kind of justifies my steps. Example 4. All right, in this one, I'm definitely going to start with the right side. As I'm looking at this, my first instinct was to do something different. If you pull the notes up for this section that I did, the ones that were completed on Google Classroom, you're going to see example 4 done a different way. Okay, and I'll tell you in a second how I did that. But this, I'm seeing something else right now that I approached it a different way when I did those notes. But so the point is here that there's often more than one way to do these. It's, as long as you're interchanging things that are equivalent and you are doing sound mathematical and algebraic processes, there's often more than one way to get there. Two different people might approach this problem two different ways, and both of them are just as good. But on this one, the first thing that popped out at me right now is anytime I see one of the functions with squared, where the function is squared, kind of let that be a trigger you to look at your Pythagorean identities. So remember the identity that sine squared plus cosine squared equals 1. So it may not be the way you want to go with it, but every time you see one of the functions squared, that you can use a Pythagorean identity. Maybe it'll work for you, maybe it won't, but it's something you can always interchange. So if I want to substitute for sine squared, I could subtract the cosine squared over and use it in this form. All right, and so wherever I have a sine squared, I'm going to replace it with 1 minus cosine squared because those are equivalent. Now, when I see this, it reminds me of the last problem that I just did. Should look really familiar. This is a difference of squares. It's kind of written a little bit reversed of what the other one was, but so I can factor 1 minus cosine squared into, let's split the 1 into 1 times 1, split the cosine squared into cosine times cosine. One gets a sum, one gets a difference. So there's no different in factoring 1 minus x squared. All right, and I'm just going to bring down. All right, and if you look at the next step, the 1 plus cosine squared, or the 1 plus cosines divide out, common factors divide out, anything over itself is 1, and I'm left with 1 minus cosine theta. And looking at what I'm trying to get to, 1 minus cosine theta, I'm done. All right, so just to go back and justify, so here, this was just a Pythagorean, I'm just going to arrow that there, that was just interchanging, substituting a Pythagorean identity. From here to here, all I did was factor. I'm not even going to say it's a difference of squares, difference of two perfect squares. From here to here, all I did was reduce / simplify, divided out the common factor. Now, when you look, if you pull up the notes that were on Google Classroom for this section and you're looking at example 4, I did that for whatever reason that day, I did that. And I just did I went a different route with it. What I did on that one is actually a technique we'll use on example 6 in a minute, because on the example 6 we don't really have a choice. What I did was I multiplied by the conjugate. The conjugate of 1 plus cosine theta is 1 minus cosine theta. So when I did this problem in the notes that are already on Google Classroom, the completed notes that is, I multiplied the bottom and top by 1 minus cosine theta. It worked fine. I still got there, just a different route. So I just want you to know when you're looking at that in the video, it doesn't line up with the notes that are already on there. It's because you'll see 2 different ways to do that problem. Okay. All right. Example 5. So in example 5, we want to prove that sine theta times cosine theta is equivalent to sine minus cosine over secant minus cosecant. All right, well, this is definitely the side I want to start with. So the top being sine minus cosine, not a whole lot I can do to that. It's already pretty much as broken down, basic as it gets. So I'm just going to bring it down. I'm going to have to kind of do my operating on in the denominator. And there's, really they're not squares. There's no Pythagorean identity I can use here, but probably just breaking them down with the reciprocal identities. So secant 1 over cosine, cosecant 1 over sine. So let's go ahead and do this one as 1 over cosine. And this one is 1 over sine. Now my next step, what I would do is just combine these together into one fraction. Okay, so how it's no different if you were doing 1 over x minus 1 over y, or 1 over 3 minus 1 over 4. I need to have a common denominator. To make the denominator the same, I would have to multiply this by cosine and this by sine. And remember, if you're changing the denominator, you got to change the numerator in the same way. Multiply the bottom by cosine here, so I'll multiply the top by cosine. So what I end up with is bring the numerator down. So I end up with sine over sine cosine minus cosine over sine. So sine times 1. And then this one's going to be cosine times 1, so it's cosine. And since the denominator is the same, I'm just going to go ahead and put one denominator under them. They'll combine to, so I'll have sine minus cosine over sine times cosine. So that's so all I've done so far is substitute reciprocal identities. And then I just combined the fractions, just subtracted the fractions. Okay, not there yet, but this is what I'm going to get to. So because if I just do the math, I do the algebra, I wanted this divided by this fraction. So what do you do when you divide by a fraction? Think of this as being over 1. So the numerator divided by or multiplied by, you've got to flip at the bottom, flip it, this reciprocal at the bottom. So sine theta cosine theta over, this becomes my denominator. Okay, and so you're basically just multiplying across, so it's this times this, 1 times that. See the common factors, those are going to cancel out, divide out, and look what I'm left with. Okay, so after I did just combined my fractions together, subtracted the fractions, I just did the division. So dividing by multiplying by reciprocal, and then just simplifying, dividing out the common factors. All right. So example 6, this is the one I said before, where you'll see the technique that I had used in example 4 when I did that in the notes that are up on Google Classroom, the completed notes. So, so when you get to number 6, you're looking at this, both sides really look equally complex as far as that goes. So it really doesn't matter what side you start with. I'll stick with the right side since I've done that one every time, but they really wouldn't make any difference. They're equally as simple. But with this one, I'm kind of, if you haven't seen this technique before, you probably would be stuck at this point because, what can you do with sine? It's as broken down as it gets. It's not squared, so I can't do any kind of Pythagorean identity interchange. Same with the cosine down here, it's not squared. So I'm really stuck here. All right, well, one trick that you can use, as I mentioned a minute ago, is to multiply this binomial by its conjugate. Remember, the conjugate of x plus y is x minus y. So the conjugate of 1 plus cosine is, or 1 minus cosine is 1 plus cosine. Now, you'll see in a second why did I do that. Okay, well, we'll see in a second why that is. But remember, I can't just multiply the denominator by 1 plus cosine. If I do, I just change the whole problem. But if I multiply the numerator by 1 plus cosine t as well, then I'm really just multiplying by 1. Anything over itself is 1, and 1 doesn't, you change the form of this, but I'm not changing the value of it. And so if you change the bottom by some multiplier, you have to keep that fraction equivalent, you have to do the top as well. Okay, so in the numerator I have sine t times 1 plus cosine t, and you may be thinking, why didn't you go ahead and distribute that out? And I may. We'll see when I get to the next step or two if I need to do that. Right now I'm just going to leave it like it is. In the denominator, I'm going to actually go ahead and multiply these together. 1 minus cosine times 1 plus cosine. Okay, no different than if you were doing 1 minus x times 1 plus x. You just multiply. So 1 times 1. Now, 1 times cosine t is cosine t. Minus cosine t times 1 is negative cosine t. So I end up with a positive cosine t and a minus cosine t. Maybe I should go ahead and write that out just to. All right, so plus cosine t, minus cosine t, and then minus cosine times cosine, so we have cosine squared t. So you can see now that these subtract out. All right, and so I end up with sine t times 1 plus cosine t over 1 minus cosine squared t. All right, and so keeping my eye on where I want to go here. The 1 plus cosine, I see that, but the sign has to go somehow. But one thing I do see, when I told you, when anytime you see that function with squared, it's some Pythagorean identity will work to substitute there. So let's go back to the one that has the sine and the cosine in it, and it is the one sine squared plus cosine squared equals 1. If I subtract the cosine squared over, it is equivalent to sine. So sine squared, that is. So I could interchange or substitute 1 minus cosine squared for sine squared. All right, and then if I have a sine in the numerator and sine squared in the denominator, this sine will divide out one of these sines. Of course, I still have a sine left because there was 2 of them. But that gives me 1 plus cosine t divided by sine t. And that is what I was trying to show. So to document my steps here, let me do it over here. I did multiplied by conjugate. And that's always a trick you can use. And all I did here was multiply the fractions together. So multiplication. Did nothing here but just simplify. Basically just let these subtract out. Did a substitution of a Pythagorean identity. So I'm going to substitute Pythagorean identity. And then just reduced. So reduced by dividing out the common sign. And I got what I need. So again, they just take practice. It's like a puzzle. You know what you want to get. It's kind of like I'm giving you the answer. You just got to show me through what steps can you convert this into this. How do you get from here to here or here to here? But if all if all else fails, try something. It may not, and many times, as much as I've done this, I might some of these, if I get a difficult one, and I may start something, and I go a few steps, and it's not going where I want it to go. I stop, scratch that, go back and start a different route, try something else. But it's like a puzzle. You got to just kind of appreciate the challenge of it. But it does take practice. It's not something you're going to just, right away know how to do. So don't be too hard on yourself. Don't give up. Stay with it. Just keep trying things, using the techniques that you've practiced. And they're not that bad with a little bit of practice. So for our last example, this one's a little different. And for number 1, it's not an identity that we're trying to prove. So this one, we're actually trying to disprove it. The directions say to show that cosine of x equals square root of 1 minus sine squared x is not an identity, which means it's not true all the time. There's a case out there where it fails to be true. And so we're going to show that by finding that a case out there where it's not true, also called a counterexample. We're going to find a counterexample where this fails. Okay. So let me rewrite this down here. So it's saying that the cosine of x is equivalent to the positive square root of 1 minus sine squared. Now we know that 1 minus sine squared, remember with the Pythagorean identities, that is the same thing as cosine squared. I've got a disagreement in my variables here, so let's just make this x, since I went with x on the other side. I didn't mean to have a t over here. All right, so no matter what angle x is, when you take the cosine of that angle, you're going to square it. It's going to be positive no matter what. And so one thing that would make this, where this would be false, would be if the cosine, because this side's not squared, if the cosine of the angle were negative. So what I need to find is an angle where cosine is negative, cosine of the angle is negative, and that would make this false, because when you square it, it's going to be positive, and this is taking the square root. So let me think in terms of the unit circle. You know, cosine is the x coordinate, so anywhere in quadrant 2 or quadrant 3. So let's just make it easy. Let's just use pi. So a counterexample would be if x equals pi, then cosine of x would not be equal to square root of 1 minus sine squared x. Okay, let's just verify that that's true. So the cosine of pi should not be equal to the cosine squared, or 1 minus sine squared, same thing, of pi. Okay, well, remember the cosine of pi is -1, 0. Those are the coordinates of that point on the unit circle, so cosine is the x value, which is -1. So the cosine of pi is -1, and we were trying to show that that is not equal to the cosine of pi squared. -1 squared is 1, and the square root of the positive square root of 1 is 1. So this says that -1 is not equal to 1. And so my counterexample pi provides a counterexample where this fails to be true. And if it is not true all the time, it is not an identity, because an identity is true for every replacement value of the variable.